Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the lecture 3 of root locus, right? So in the previous lectures, firstly we understood like what was a root locus, and we gave you a brief overview about the rules, and then we understood the magnitude and angle condition, right? For my OLTF to satisfy. Okay, and through that we did few questions in the previous lecture 2, and in this lecture I will go from complete scratch from rule 1 to rule 6. Okay, and we'll sketch our root locus with the help of a OLTF and my variation of system parameter k. Okay, but obviously few step I will skip, one step I will skip, right? Because I will tell you the reason there. That step will be covered in another example, don't worry. Okay, so yeah, this is the question basically the example that we have to plot the root locus of the following OLTF. So we have been given a OLTF and we have to plot the root locus for this one. Okay, so as you can see, I have this is a OLTF, right? So I have one open loop 0 and two open loop poles. What can I say about the virtual 0, right? So I hope you remember, right? So number of virtual zeros will be number of poles minus number of zeros, number of open loop poles minus number of open loop zeros. So I will have at least one virtual 0. Why? Because as k tends to infinity, I should have two CLTF poles, right? As my order of my characteristics equation is 2. Okay, so I will get one of them from this s equals to minus 8, right? But other one will be tending to infinity. That's the magnitude, but in which direction we don't know, we'll see. Okay, so yeah, what does the rule 1 say? Rule 1 says we have to locate the open loop poles and open loop zeros and poles in the complex plane. So firstly we have to locate those two, right, in the complex plane basically. So why is this important? This will tell us about the starting and ending point of a root locus. So it's very important to firstly know where my root locus starts from and where does my root locus ends at, right? These two things are important. Now note that each of n curves in the root locus will start from open loop pole for k equals 0. By n, like n, what is n here? N is the number of open loop poles. So let me write here, n is the number of open loop poles. Okay, and what is m here? M here is number of open loop zeros. Okay, so this is my n and m. Okay, so now what is this telling? That my n curves, right? I will have n curves, right? N branches. I hope you remember that, because I have n roots, right? So n curves will start from, for k equals to 0, from those open loop poles. So like each open loop pole will start from n curves. I will show you, right? So out of this m curves will terminate at open loop 0. Like out of this n curves, whichever are terminating, right, they will whichever starting, they will terminate. Out of this, m curves will terminate at zeros, at will terminate at open loop zeros, because I have only m open loop zeros, and the other n minus m will terminate towards infinity in the complex plane. Now the direction we don't know, we'll see. This is just the written portion. We will see this when we draw this. There you will understand this in a better manner. So how many number of open loop poles do I have? So firstly, open loop poles. How many number of open loop poles do I have? So open loop poles equals to 2, right? I have 2 open loop poles from here, right? Order is 2. Okay, that I can see. So I will copy this one and just paste it there so that it's easier for us to visualize. I have 2 number of open loop poles. Now how many number of open loop zeros do I have? So open loop zeros, right? Open loop zeros equals to 1. I have only one open loop 0. Now how to check, what is this telling us? Like these are my starting and ending points, right? These are my starting and ending points. So let me first draw the axis. This is my sigma and this is my g omega. This is for my closed loop poles, right? Closed loop poles. So where are the roots located? Poles located. Poles are located at s equals to -2 and s equals to -2 and s equals to -4. I hope you understand, right? So s equals to -2 and s equals to -4. Okay, and where is my 0 located? It is at s equals to -8. Okay, s equals to -8 is my 0 located, right? So if s equals to -8 is my 0 located, then these are my directions. So what will happen? From this poles, my two curves will like start off. Okay, start off, then it will terminate. One of them will terminate here and other one will terminate to infinity. Now what like where to infinity, we don't know. Like one of them will terminate to here and something will terminate to infinity. Now in which direction? Here it can be the virtual 0, here can also be the virtual 0, or the virtual 0 can be here also. That we'll see. Okay, that when we solve, we'll see. Okay, so like how to locate this, right? How to locate, like how do you understand that this will terminate here and or start from here? So let's do that. So basically, if I copy this equation, if I write my equation, that what the root locus will have two branches, and why we'll see. The root locus will have two branches. Okay, the root locus will have two branches. Why? Because order of characteristics equation, which is basically the denominator of my transfer function, right? So that defines my number of roots or number of poles, and that will define my number of branches, is 2. So what is my characteristics equation? What is my characteristics equation? It is basically 1 plus g of s, which is equals to 1, sorry, this is equals to 1 plus g of s equals to 0. Okay, this is my characteristics equation. Okay, so yeah, this is basically my characteristic equation. Now what does this become? So from here, what can I say? Now I will take for two conditions. So first case, I will take the first case, which is case 1. Already I think I have explained, still I am explaining it more elaborately, that if my k tends to 0, okay, but this has actual no significance. K cannot be actually equal to 0, but I have to start the root locus from somewhere. So if my k tends to 0, then what will this characteristic equation look like? So what I will do, I will cross multiply s plus 2 into s plus 4, and this will become k into s plus 8 equals to 0. Now if my k is tending to 0, okay, k is tending to 0, then what will happen? Basically, if my k is tending to 0, then basically I will only be left with this equation, right? So this I can write as s plus 2 and s plus 4. So I will have two solutions for this one. So one is equals to 0, one is s equals to -2, other one is s equals to -4. Okay, other one is s equals to -4. So I have two solutions for this one. So now right now what do I see? So if k is tending to 0, then my open loop, I've already told this also, my open loop poles will be equals to my closed loop poles. Okay, so this is what I know if my k tends to 0. Okay, so I got my two solutions, and hence since here is where my basically root locus originates, right? So here, right, what will be the values? The values here will be k equals to 0. Okay, I mean the system parameter value will be k equals to 0. Okay, now let's see if here really the value is k equals to infinity. Let's see that, right? So now we'll go for the case 2. So what does the my case 2 say? Case 2 says that my k should tend to infinity. K should tend to infinity. Now if my k is tending to infinity, then what will happen? Then basically again what I will do, right, that I will write this equation. This time I will divide by k and multiply by this also, obviously I will do, but also divide by k is equals to 0. Equals to 0. Okay, so here what can I see? If my k is tending to infinity, this will go to 0. If my s is finite, and if k is tending to infinity, then this will go to 0, right? So now what can I say? That if k tends to infinity, this can limit k tending to infinity, this can go to 0. Okay, this can go to 0. Then my s plus 8 will be equals to 0 and s will be equals to minus 8. So I get one solution, right? S equals to minus 8. Now you might ask where is the other one? I have also another pole of the CLT, right? I only get one solution. That we'll see when we do the asymptotes, right? Angle of asymptotes, that we'll see. So yeah, basically that is how I locate my open loop 0 and open loop pole. So here, right, value of k is infinity. So after this, what we do? After this, we go to the step 2. We locate the root loci on the real axis. Okay, this is determined by the open loop poles and zeros that lie on the real axis, basically. So how do you determine that? So basically, right, like we are only concerned with the real axis for now. What is the real axis? Real axis is this one, not the complex conjugate plane. Okay, we'll obviously do that also, but for now I'm only concerned whether my test point, whatever I choose, if I choose a test point here, will it lie on my root locus? So is it a valid test point? Okay, is it a valid test point? Will it satisfy my angle and magnitude condition? Okay, so that is what we have to do. Okay, so basically this like if the total number of real open loop poles and real number open loop zeros lie on the right of the test plane is odd. Okay, this is like a thing to remember. Okay, very good thing to remember, that if let's say you choose the test point here, and to the right of test point the total number of poles and zeros, adding both of them, are odd, right? Odd, then this will be a valid test point. And if it isn't odd, then this will not be a valid test point. Okay, so why is that? Obviously we'll go to the like intuition why is that the case. But let's say here, right, what is my let's say here, what is my total number of poles and zeros on the right of my test point? It is 3. So if it is 3, then what will happen? Then basically this point is a valid test point. This will lie on my root locus. Okay, why? Let's see. So first, like this, I hope you got that there should be odd. So this is a very, very important thing and very useful thing. Obviously you have to remember this, but the explanation I will obviously give, right? So what do? Basically we take test point st and check whether it satisfies my satisfies basically angle condition, because for any value of like k, I can satisfy the magnitude, right, if it satisfies the angle condition. So basically I am only concerned with the angle condition. Okay, mainly angle condition, because it is independent of k. So that test point will only lie on my root locus if it satisfies my angle condition. So satisfy my angle condition. So what is my angle condition? Basically my angle condition is this one, right? GST into h of st equals to minus 180. It's a odd multiple of 180 degrees. Okay, it's a odd multiple of 180 degrees basically. So k can be anything, 0, 1, or okay, basically we're adding 360, subtracting 360, which doesn't make any difference, right? So yeah, I hope you understand, right? Now why is the case, one thing I skipped here is that what is this statement saying? Choose a test point on the real axis if the total number of real open loop poles and real open loop zeros that lie to the right of this test point is odd. So it is talking about the real, right? Real ones. Okay, we are not concerned with the complex conjugate ones. Why? So one question is, why the roots, okay, let me that lie on the real axis, okay, real axis are determined by only open loop poles and zeros and not complex conjugate. Sorry. Okay, why is this a case? Why is this a case? Because I'll just take it to the next page. Okay, or I can write here also, as the overall angle contributed by complex conjugate poles will cancel each other. Either they will be 360 or 0. Okay, so as, okay, I need to take it to the other point actually, else I will not be able to finish this one. So let's take a new page. As the angle contributed by the, okay, only, sorry, not only real, I should also write only real open loop poles and zeros. Okay, I don't have space, so what I'll do is, as the angle contributed by the complex open loop pole, complex open loop poles and zeros will cancel each other out. Okay, so the total angle contributed by them will cancel each other out. Why? Because they are in conjugate format, as they will be present in conjugate form. Okay, as they will be present in conjugate form. Why? Let's see. Okay, let's take an example and there we'll see. So let me draw the sigma plus j omega plane. Okay, this is sigma and this is j omega. Okay, sigma and j omega. So now, right now like let me take an example of complex conjugate poles. So I have complex conjugate poles here, okay, and this is my ST test point here, let's say. So what is the angle between this ST for the two complex conjugate poles? This is the first one and this is the second one, right? Okay, first and second one. Now what is the angle we measure with respect to my positive x-axis, right? Positive x-axis, okay, that you have to remember. So this is my positive x-axis and this is the angle that I measure. So what is this angle? So if I know, like if I know somehow the height, okay, y point, this is, let's say this is my y distance, right, and this is my x distance, right? How can I measure the x distance? X distance is this one, right? It's this one basically. So I will write it in a very small manner here, that this is my x distance, okay. So y is this one only and x is this one only, but this x is same for this one also, right? X is same for this one and y is also same for this one. I'm talking about the distance, I'm talking about the magnitude, okay, talking about the magnitude. So both of them are same. So now can you tell me like what will be this angle basically equals to? So if I can find this angle, right, if I can find this angle, this will be 360 minus this angle, right? So I have to find this theta, okay. If I find this theta and I can get 360 minus this one will be my angle, okay. So this is my, let's say, P1 and this is my P2. So what is the angle contribution of this theta P2 in this point ST? So theta P2, right, I can write equals to, so as I am going the clockwise anti-clockwise direction, it will be 360 degree minus theta, right? If I would have gone clockwise, it would have been only minus theta, okay, anything you prefer, but sign you take care of, okay. So now, sorry, this is not theta P2, this is theta P1, okay. So yeah, now what is theta? Theta will be basically what? This tan inverse height upon base, right? I'm talking about the magnitude only, So theta, like we have done this like in the coordinate axis also, okay. Tan inverse mod of y upon mod of x, okay. So this is what my theta is equals to. Now let's calculate the theta P2, right? So what is my theta P2? Theta P2 is basically, simply I'm with respect to the positive x-axis, this is the positive x-axis, which is basically plus theta, right, plus theta. So which is equals to theta itself, okay, which is equals to theta itself, right? So these two are same, okay. I will not derive the y over x. So what is the total angle contribution? What do? We used to add those angles, right? Because these are poles, right? These are poles. In the denominator, if there is poles, they used to get added. We'll solve this one, then we will also understand that theta P1, like what is the thing? What do you used to do? So angle of G of H of S was simply, if you remember, right, if I have zeros at the top, so like zeros used to get added and the poles used to get subtracted, right, as they are in the bottom, right? So I hope you understand that if there is a division, obviously it will get subtracted, theta P1 plus, but these will individually get added and overall get subtracted to a 0, okay, and okay. So hence we'll add these two, okay, we'll add these two and check what is my value coming. So hence theta P1, theta P2 equals to 360 degrees, right? Theta P1 plus theta P2 equals to 360 degrees. Now if my theta P1 equals theta P2 is 360 degrees, I can also write this as 0 also, okay, like 0 also, or what I can write as 360 into 2k, right, where k can be 0, 1, 2 and okay. So k can be any multiple. So what I can observe is, due to complex conjugate poles, the angle contribution is a even multiple of my 360, right? So it will not make any difference, because 360 means a full rotation, okay, and it does not make any difference. As I told earlier, right, if you add an angle with 360, it will not make any difference. Okay, sorry for the noise and outside, if some noise you are getting. Okay, so I can write the statement here. The angle contribution due to any point on the, this is on only for the real axis, because what will happen if I have a test point here, so what will happen, this theta will change, right? Due to this test point here, this y distance will be reduced and this y distance will get increased, then my theta won't be same anymore. So that's why this is not valid for any point here. This is only valid for real axis, because in real axis my x and y both are symmetrical, right? Because my conjugate poles will be symmetrical, right? That's why. So yeah, so the angle contribution due to any point on the real axis due to complex conjugate poles, on the test point will be even multiple of, sorry, this is actually okay. I can write pi also, sorry, I can write pi also, or even multiple of 360. I can write 360. Okay, so yeah, what I can write is, okay, yeah, even multiple of, okay, sorry, this k, right? K can be anything here, right? Doesn't need to be 2k, so k can be anything, sorry, will be a multiple of, not even, will be a multiple of 360 itself, right? Hence it will not make any difference. Okay, hence the complex conjugate poles won't make any difference. Hence because that is not affecting my angle condition, because you add anything with 360 and add angle with 360 or subtract angle with 360, it doesn't make any difference. Hence the complex conjugate poles won't affect my angle condition for real axis. Okay, so yeah, this was for the basically real axis part. Now let's actually solve this, right? Let's actually see, apply the rule too. So where were my poles? Basically, and open loop poles and zeros. Let me copy that one first. So here were my open loop poles and zeros. Okay, I will copy this one. So according to the rule, okay, now I will check the rule for the odd case, right? It told us about the odd thing, that total number of poles and zeros should be odd on the right hand side, right, of my test point. So here what I know, from -4 and -2 my root locus will originate, and at -8 it will what do you say, it will terminate, right? Now will my root locus be like this one, or it will go like this one? Okay, what will happen, that also I have to decide, right? Okay, so if you want to say that sir, my root locus can originate like this one also, right? Like this one also it can originate. Okay, you can say that. Like, why are you saying it will lie in the real axis? It can lie here also. Okay, lie here also, right here, lie here also. So if you say that your root locus originates and directly goes to the complex plane, then what other thing you have to say? What is the other thing you have to say? The other thing you have to say is that as my coefficients are real, right, of the characteristic equation, then if the root locus originates like this one, so what does this represent? This represents complex poles, right? Hence I will have a conjugate also, conjugate pair also I will have. Now if I have a conjugate pair, then how many roots do I have? I got two roots, right? I got two roots, but here also some roots will originate from here, right? Okay, some here roots will also originate, but maximum I can have only two roots. So maximum branches I can have only two. Okay, but you have already taken this one, so how, from where will this originate? So here also I need to originate some root, right? Some root from here also it will originate. So this solution is not possible. Like it can't directly originate to complex plane directly. It is true for this one also. If I take this one, then here also I have to get some pole, right? And which will not come because maximum branches, this will eat up the maximum number of branches here and here, right? So we have to be careful about that. Okay, so yeah, that is the first thing that I wanted to mention. Now what is the next thing? Next thing is, as there it has mentioned that total number of poles and zeros should be odd. So let's take test point in each of these zones, right? Each of these zones, let's take test point. So I will just delete this k value for now. Okay, and I will take the test point in each of these zones. So here let's say I have a test point, here let's say I have a test point, here let's say I have a test point, and here let's say I have a test point. Okay, so in the 4 points I have test points. So now how do you measure the angle? Okay, we measure the angle with respect to the positive x-axis. So this is my positive x-axis, and this test point, right, is ahead of all of them. So if I want to go in the anti-clockwise direction, okay, basically it will be on this axis itself, so this will be 0. Okay, I will name this as, okay, st1, st2, st3 and st4. So theta st1 equals to 0, total angle contribution basically. Okay, total angle contribution due to all the poles and zeros, right? Now if I do it for theta s2, what is happening? This -2 is ahead of this one. So if I want to go from -2 to theta s2, what I have to do is like this, right? Like this I have to go. So if I want to go like this, obviously I'm rotating a full 180 degrees in the anti-clockwise direction. Okay, but all of these poles and zeros for this theta s2, right, they are all in the positive direction. So theta s2 will be 180 degrees due to -2. Okay, now what is my theta st3? What is my theta st3? So again, right, now this is st3 and here this is only ahead of this one. Okay, hence the angle due to this 0 is 0, but these two poles are behind of this one. So I have to, like, sorry, these 2 points are ahead of this st3, so I have to go behind to reach to st3. So this has to rotate a full 180 degrees. So you have to rotate a full 180 degrees, and this has to also rotate a full 180 degrees, right? So what will be the case? So this will be 180 degrees and plus. So as I did that just to make you understand, you have to go to the behind. So if you have to go to the behind, you are rotating in the 180 degrees. If you are looking in front, so what is the angle? Angle is 0. So like this 0, this st3 point is ahead of this 0, right? So I'm just looking ahead. I don't have to rotate my head. Now this st3 point is behind these poles, right? So I have to look behind. So I'm rotating in 180 degrees, right? So that's why these are 180 degrees. Okay, so I get here 360 degrees here, right? So now this is due to -4 and -2. Okay, now this theta st4, what is the theta st4? So theta st4 is here, right, and all of them has to rotate behind it. It is behind everything, so it will be simply 180 plus 180 plus 180. Basically this is 360. Okay, I can write this as 180 only. Now do you remember one thing? What was my what was my magnitude condition. Like these, what are these? Theta st1, st2 are all basically, theta st is basically angle of g of st, h of st, right? That is what basically this theta st equals to. Now what does this needs to follow? This needs to follow angle condition, right? So what was my angle condition? Basically theta st should be equals to odd multiple of 180, right? Okay, odd multiple of plus minus 180 or whatever you want to say. Okay, so now which ones are satisfying? But I can say this one isn't, right? So it can't be 0, it has to be minus 180 or plus 180. This theta s2 is satisfying, so theta s2 is satisfying, st2 is satisfying, and my theta st3, no, it is 360, it is equivalent to 0 degrees only. This is satisfying, right? Theta st4 is satisfying, so theta st4 is satisfying. So here it is satisfying. Like here, all of the points whichever I choose, all like behind the poles and zeros satisfying, and in between these, right, st2, in between whichever point I choose, satisfying. So what does this mean? What special thing you notice? You notice that ahead of this test point I have only one pole, and ahead of this test point I have only 3 poles. So yeah, that statement is correct. So if I have total number of poles and zeros odd ahead of my test point, so it will lie on the real axis. This is only for the real axis condition. Okay, so yeah, so basically that is basically what we did, right? We found out the real axis point. So my location of root locus, so root locus will lie between S, basically, okay, I will not write like this one, between minus, okay, I will write minus 2 to minus 4 and minus 8 to infinity, right? Okay, only for this is only for the real axis, only for real axis. Okay, this is only for real axis. Okay, so now right now basically what we'll do, we have to determine the like this step is done. So we have plotted the real axis root point. So let me also highlight this one. Okay, I will copy this one, okay, and highlight this one, then you will understand it better. So I will take another page. What I will do is I will take this one. Okay, I can't take this one. First paste this one, then I will take this one. So this one will be this one. Okay, this is the point where I will lie, and this is also the point where I will lie. This is the regions, right? These are the regions. Okay, and it will go on till infinity. Okay, and this infinity is giving you the hint, basically it is a virtual zero. Okay, this will be the virtual zero, and this will be the asymptote. This is the next step. Basically this is a great segue to the next step. So yeah, this will be asymptote. We'll see. Okay, what is this? This is asymptote, basically the virtual zero, as you say, right? Okay, so yeah, this is now I got my location of root locus in the real axis. Now let's go for the determination of determining the asymptotes. So to determine the asymptotes of the root loci, this step applies only when m is less than n. Okay, obviously when my number of zeros is less than number of poles, then I will get asymptotes, basically the virtual zeros. Else if they are equal, so if k tends to infinity, I will terminate to m zeros, right? M open loop 0, so that is not an issue. So there won't be any virtual zeros there won't be any asymptotes. But if my number of zeros is less than number of poles, then there will be asymptotes basically, and that is what basically I'm interested in. Okay, so if the test point is chosen very far away from the origin, the angle contribution of each pole, okay, each open loop pole and 0, I think, okay, each open loop poles cancels with that of open loop 0. Yeah. So those angles are almost same, right? Those angles are almost same, and those cancel each other out. So we'll see what does this statement mean. So basically, right, okay, before going into the asymptote, what I want to say is like key points about asymptote. So I left about this part from here when k was tending to infinity. Where did it go? Here, right? When k was tending to infinity. So I will come back to this part now. So now case 2 continued, right? Continued. Okay, case 2 continued. So what is basically the case 2 continued? So case 2 continued is basically what do you want to do is basically, right, you want to make k infinity. Now if you make k infinity, we only get one solution, but I want two solutions. How to get that basically? So what you do is you write the equation like this one. Okay, so you delete this one, and what you do is you write s plus 2 into s plus 4 divided by k into s plus 8, and this plus 1 equals to 0. Okay, so what is the point here is if my k is tending to infinity, okay, and this s are finite, okay, if k is tending to infinity and s is finite, then what will happen? My denominator is going towards infinity, very high, and this is finite, numerator is finite, so this will go to a 0. So it will become 0 plus 1 equals to 0, which is not possible. How is this possible, right? How is this possible? Not possible. So what is the problem? The problem is I have to make my s also go towards infinity. I have to make my s also go towards infinity, then only this equation will get satisfied. Now for this particular case, in which direction my s should go? Okay, in the direction of minus infinity. So if I put my s tending to minus infinity, okay, you solve this equation. I hope you solved this like limits multiple times. If I put s tending to minus infinity and k tending to infinity, okay, then what will happen in this same equation, right? Let me copy this one. Basically this will be minus 1 plus 1, which is equals to 0, because this will go towards minus 1. Okay, because this like infinity times infinity, fine, infinity like the here order is same, here also order is same, but infinity times minus infinity, this is in the bottom is minus infinity square, just like think like that only, minus infinity square. Or what you can do is simply you can divide by s and k, right? That you can do. Okay, like that you can solve. Okay, I will not solve it, this is not limits class. Okay, I will not solve. So if I put my s tending to infinity, then I will get basically what do you say, minus infinity, then I will get satisfy this equation. Okay, so my s tending to infinity is a virtual 0. Okay, and we will understand more about this slowly. We will solve more questions and this will also get more clearer. S tending to minus infinity is a virtual 0 basically. Okay, so this is what my s tending to minus infinity is. Now let's read the points. So what this was the first like key points about the asymptotes. The intersecting point of the asymptote on the real axis is called centroid. So in this case, right, my asymptote is minus infinity, so it is in the negative real axis on towards the infinity on the negative side. Okay, in this case my asymptote is lying on the real axis itself, but few cases and in most of the cases my asymptotes don't lie on the real axis. Okay, like few like in other cases also my asymptotes may not lie on the real axis. So why they will lie? They will lie somewhere like here. Okay, somewhere like here. Now if I just connect those two asymptotes and this point, right, this point, because asymptotes will obviously, if they lie in the complex plane, they will be in the conjugate format, right? Conjugate format. So I will understand it again, right? That concept, right? So if anything is in the complex conjugate plane, they will be in the conjugate form. Sorry, if any one pole is in the conjugate plane, then the other one will also be present. So if I connect these two, right, intersecting point with the asymptotes, that point is called my centroid. Okay, so this when we will solve, we will get, but here in this case we won't have a centroid. Why? Because my asymptote itself is not lying in the complex plane, it is lying on the real axis, negative side, so we won't have any so we won't have a centroid, right? So next, the point from which the asymptote originates is known as the centroid. Okay, like that also you can call that, like if this is my asymptote, okay, these are just points, not that important. So from here we can say from centroid it is originating at asymptote, but these points, the dot points, these are actually not my real root locus point. These are just some straight line. Okay, so no need to worry about this one. Okay, this is mainly about centroid. Centroid can be located anywhere in the real axis, which may or may not be a part of the root locus that I was talking about, right? Centroid can be like in anywhere of in the real axis of the root locus. Centroid will lie on the real axis itself only. Okay, but it may or may not be part of the root locus. We'll solve more examples and we'll see this. Okay, these are just few key points. Okay, so how to find asymptotes, basically how to find asymptotes. So first let me take the open loop poles and zeros and that Sj omega plane. This one let me take. Okay, if I take this one, will it work, or I should take this one? So how to basically find the angle of asymptote, basically like this, right? We have to find the angle of asymptote, right? Determine the asymptotes we understood that it is in the negative infinity. Okay, but how to, like, we have to determine the asymptote, basically the location of asymptote we don't know, but we have to find the location of asymptote. How to find that? So basically what you will do, okay, we don't know. Here I know that it is s tending to minus infinity. Let's say we don't know. So let me choose asymptote. Okay, this is gone. Even this is not valid. Okay, I will still choose this one. Let's just wait 1 second. So let's say my asymptote is lying over here. Okay, because I will have only one virtual zero, right? But it is not possible to lie over here because I need another virtual zero here also, complex conjugate, right? But still, let's say I'm choosing, okay, I don't care about you, I am not listening to you, I'm choosing my asymptote here only. Okay, so if I'm choosing my asymptote here only, then what will be the angle contributions due to all these three? Let's check, right? So here again, right, I will connect these poles and zeros with this test point. So what is the point I'm telling is, like, what is the step? Basically choose a test point. Okay, I forgot to write. Choose a test point ST really close to my asymptote. Okay, really close to my asymptote. So let's say my test point is lying around here. Okay, this is my ST, right? Very close to my asymptote, and my asymptote is lying around here. Okay, no issues, my asymptote is lying around here only. So like, okay, let me write this in single line, that will be easier. Okay, so choose ST, like choose test point ST. Okay, I should write test point also. I have to write so many things. Let me bring this to the bottom. This I can extend, right? Really close to my asymptote, basically close Okay, so I am assuming my asymptote is here, even though it's not possible, but still I will assume this one wrong only, and I am assuming my test point is here. So I will measure the angle contribution due to all of this, right? Due to all of this, I will measure my angle contribution basically. Now I have to measure the angle of asymptote, basically that is the main thing. So angle between this test point and asymptote will be what? It will be 0, right? Because it is very near. Okay, it's, if something is very near this pole, what is the angle contribution due to this pole? 0. It is on that point only. So that is what I am assuming. So angle, okay, I'll let me reduce this size of this one. This is taking too much size. Angle between asymptote and test point is almost equals to 0. Okay, equals to 0. They are almost equal, right? Okay, so yeah, now what is the main condition for this test point to lie in the root locus? What is the main condition? Okay, basically I am finding my trace of like root locus to go towards my asymptote, so it will terminate at t like infinity, right? K equals to infinity. So I'm trying to trace that. So once I finish my proof, then you will understand. So this I'm just giving you an intuition, not anything else. Most of the teachers what they do is directly say you the rule. Okay, just mark that rule. Still I'm giving you some intuition. Okay, even if you don't understand this, this will not affect your gate performance, because what in the end you have to do is remember the rule, but this may help you in remembering the rule. Okay, so that's why I'm proving it to you with bit of intuition. This is not the complete proof, just slight intuition. Okay, so yeah, main thing is remember the formula. Obviously when we will solve question, there will understand what things you have to keep in mind and what things you can avoid also. Okay, so now basically the main condition for ST to lie in root locus. What is the condition for my ST to lie in root locus? So basically my, what is the condition? Okay, you now it's like mugged up. I think GST into H of ST equals to 180 degrees or odd multiples of 180 degrees, right? So yeah, this you can do. Okay, so it should follow the angle rule. Okay, as k tends to infinity, so like this asymptote, right, is at k tends to infinity, as k tends to infinity. Okay, as k tends to infinity. So now right now basically what is my g of s into h of s? So my g of s into h of s basically basically my g of s is k times s plus 8 divided by s plus 4 into s plus 2. Okay, this is what my g of s into h of s is. Now what are my angles? So this, right, what will be my angle? Basically angle condition is let's say this one actually as, let me say this one as like this will contribute theta 1, okay, and this will contribute theta 2, and this will contribute theta 3. Okay, each of these poles will contribute theta 1, theta 2 and theta 3. So what will happen again, right? I hope you know how to calculate the angle of complex numbers. So this will be theta 1 minus theta 2, I can take common, plus theta 3. Like this it will come out, right? And this has to be equals to 180 2k plus minus 1. Okay, 182k plus minus 1. Now what is the interesting fact here? Now if you take this one very far away, right, very far away, what do you see? In fact, if I am, okay, let me do it like this one. Let me copy this one. Okay, again like here, if I make this one very big, right, okay, not very big, and like make this one very small, and make this one very small, and take this one very far away, very far away, what do you notice? Like the angle all of them will be almost similar, because this distance will be negligible with respect to y-axis. Okay, with, or if you want to like take this one here also, okay, here also, if you take this one here, what you will see is like this y distance, right, will almost be same for all of them, okay, and like this this will be almost zero, okay, almost zero. So here if you see all these things, right, see all these things, the angle will be almost same, like the angle contribution due to all of these three will be almost same, which is equals to my theta asymptote. That's where my asymptote is lying, right? So if I take this one very far away, like this x distance, right, this x distance is almost negligible because this is at infinity and they have some finite distance, like this is 4, this is 6, but it is negligible with respect to this infinite distance. So I will explain. So here, right, let's say here this is my x distance, and what is this distance? This is x plus 6. Now if, and this is my y, right, y, and that is how I will measure my angle, tan inverse y upon x. I will understand, right? Now if my x is tending to infinity, okay, then this 6 doesn't even matter, okay, then this x can cover this whole point, okay, whole point, it doesn't even matter. So my x is tending to infinity, then basically my like angle for all of them will be same only, okay. So I hope you got the point. That's why like took you like I taken one something like this. So as I will just write the theoretical point, but explanation I hope you got, right? As, let me write this in for this, okay, no, not that. As, okay, my asymptote will lie very far away from the poles and zeros. Basically my theta 1 equals to like magnitude of theta 1, magnitude of theta 2 equals to magnitude of theta 3 equals to, I will name this as theta asymptote, okay, theta asymptote. Now I will replace this in this equation, right, replace this one in this equation. What do I get? So my angle of g of s will be equals to, this one will be theta asymptote equals to 180 into 2k plus minus 1. So my theta asymptote will lie in the odd multiples of 180. So what does this mean? This means basically lying in the minus 180 degree axis only. So this means lying on the negative side of the real axis. So that is what we already knew, right? We put s tending to minus infinity and we got our equation solved. So from here also you can understand. So asymptote will lie on the negative side of real axis, will lie on the negative side of the real axis, right? So my asymptote will lie on here, okay. So now how do we relate this with formulae, right? So the formula of this one is basically this one. So theta asymptote, if you ever want to find the asymptote angle, right, it will only exist if there is no like number of poles is more than number of zeros, then only we will get asymptotes. So it will be plus minus 180, okay, this is the perfect formula, which is 2k plus 1 divided by n minus p, or sometimes what people prefer is p minus z, right, to understand that this is representing poles and this is representing zeros. So you can write like this one also, 180, okay, this is a complete formula, 2k plus 1, okay, divided by p minus z. You put plus minus here or inside like plus minus, it doesn't matter, okay. So okay, sorry, so basically can you relate this here? How many number of poles we had? We had 2. How many number of zeros we had? We had 1. So 2 minus 1, which is this, we are getting this only. So that's what we exactly got here, right? Okay. So yeah, I hope that cleared you a bit of doubts how to solve all these things. So yeah, this is the formula. This you have to remember. Okay, this is very important. This you have to remember. This you have to remember. So like there is another formula about the point of intersection of asymptotes on the real axis, basically the centroid. Okay, now I will not derive it. Okay, I will derive it. Okay, but I will derive it in the example where centroid is present. So that I will not derive it here, I will derive it there only. Okay, so I will just write the formula for centroid as it needs to stay in the same place. Sigma c, okay, intersection point of intersection of asymptote on the real axis. So basically the centroid, right? So what is my centroid equals to? So my centroid sigma c will be simply equals to sum of the real parts. Okay, I will not write this like 2 minutes in details. We'll explain this one. I'm just writing the formulas, and later we'll explain this one in details. This will be number of poles minus number of zeros. This one you have to remember. But for this case, why I don't have a centroid? Just think why I don't have a centroid in this example. Because my asymptote itself is lying in the real axis. Okay, that's why obviously there won't be any intersection, right? It is itself lying in the real axis. If it would have been in the complex plane, then obviously there would have been some intersection in the real axis. Okay, don't worry about this one. We'll come to this one in next example, right? So now let's go to the step 4, basically about determining the breakaway and break-in points. Now what are my breakaway and break-in points? So like what is a breakaway point? Let's understand first what is a breakaway point. A breakaway point, for example, will exist on the root locus between two open loop poles on the real axis with no open loop zeros between them. You didn't understand anything, so don't worry. Okay, just read these two. Okay, and we'll understand when I solve it. So here let's see, a breakaway point is the point from which the root locus branches leave the real axis. So it leaves the real axis, right? When the root locus branches leave the real axis, then that point is known as the breakaway point because it is breaking away from the real axis. Okay, breaking away from the real axis, that's why it is called as breakaway point. Now multiplicity of poles at this point is more than 1. Okay, we'll understand why. Okay, we'll understand. It is also the point where value of k will be maximum. This also we'll understand. So maximum value will break into 2 parts. Okay, basically local maxima, just hold on a second, it will be local maxima. Okay, this is also we'll understand. The point at which root locus moves from real axis to complex plane, that point is referred to as breakaway point. This is a definition, right? So why, how, we'll understand. It moves from the real axis, it goes to the complex plane, so it has to go to the complex plane at some point of time, right? For some value of k. So for that value of k, whenever it goes from the real axis to the complex plane, right, it is known as the breakaway point. Obviously I will explain it to you with drawing and all those things. There we'll understand better. And okay, this is actually break-in point, not breakaway, sorry. Break-in point is break-in point is the point from which the root locus branches enter the real axis. So it basically enters into the real axis from complex plane. Okay, that is what my break-in point is referred to as. Multiplicity of zeros will be again more than 1. We'll understand this. It is also referred to as where k will be my local minima. This time k will reach to its minima value. So k will be local minima, right? That is, whenever k reaches its minimum value, the root locus will break into 2 parts. Okay, it was breaking away into 2 parts. Okay, now it will come together. Okay, break into 2 parts. Okay, this will come together basically, or I can say not break, come together, or yeah, you can say break into two parts also, it doesn't matter. The point at which the root locus moves from complex plane to the real axis is referred to my breaking point. Basically from complex plane it is coming into the real axis. Okay, we'll slowly understand by visualizing it, then you will understand, then like you will get this concept in your brain, right? So let's understand what is a breakaway point. Let me basically explain what is a breakaway point. So what is a breakaway point? Breakaway point basically means breaking away from real axis. So breaking away from real axis. So you might say, sir, why is there any breaking up? Why do we need to break up? They were so good together, but why do we need to break up? So breakup happens, and that's just the rule of the life, right? So they have to break up at some point, like if it doesn't work out. Okay, so yeah, jokes apart, so let me copy this basically that root locus in the real axis, and from there we'll understand. So this was my RL in the real axis, right? Root locus on the real axis. Okay, this was my asymptote. Okay, now we'll do it for the complex plane. So if I copy this one, breaking away from the real, right? So I didn't write this very well. Breaking away from the real axis. So breaking away from the real axis. Okay, so let me cut this test points. Okay, let me cut this test points. So basically what we see is, like, one thing is this. Okay, this will have two branches, right? Two branches. So let me delete this one first. Okay, so let me color the branch that is living from my -4 pole, right? -4 pole as blue. Okay, this is living like this one, and let me color this, which branch is living from -2. I will have two branches, right? -2. Let me color this in green. Okay, but at some point they have to meet. Some point they will meet, come together, talk. Then what will happen? Then there will be anger issues. Okay, there will be dissimilarities, and then they will break apart. So basically, once they meet over here, let's say this is the meeting point, right? This is the meeting point. Okay, they meet over here. What happens? The one like this one pole and one pole becomes together, they become two, right? They become two. So that's why this point came, right? The multiplicity, okay, at this point is more than one. Basically they become two. So I have more than one poles. Basically multiplicity means the same pole is repeated, right? If multiplicity is basically two, that means two poles are repeated, right? Two poles are repeated. So here I have same poles, right? Because I am the same location. For one value of k, I'm the same location, and here two branches are present. Basically two poles are present. So here two poles are present. Okay, two poles are present. Now what will happen? Now breakup will happen. Okay, two poles are present. So basically they didn't like each other, so they went away. So basically why? Because as I have two poles, right? Now you might ask, sir, here you told us that no, this can't go into the complex plane, because if one of them goes to this complex plane, right, I will have to have a complex conjugate pair here also, but this branch is living from here. So at max I can have two branches. This is taking the two, eating up the two branches. This here I don't have another branch to give it to this one. So no, this is not possible. Here also same thing. If I, like, from here, if some pole leaves over here, I have to have another branch leave from here. So this -2 is eating up two branches. So hence, like, it is not possible to give me another branch to this one. So that it will become three branches, which is not possible. At max I have only two branches. So now if they meet over here, I have two branches, two poles at the same point. So if one of them leaves over here, the other one can leave over here, right? They have the option, they have the flexibility. So basically I have two poles over here, so both of them can leave, right? Both of them can leave in opposite direction. So that's why they will become complex conjugate. That's why they are moving in the complex plane. Okay, so I hope this point is clear to you. Okay, so here two poles are present, and hence like multiplicity is 2. 2, and here, right, the diversion happens, breakup happens basically. So here diversion happens. Okay, diversion happens. So now how will the diversion happen? So that I don't know. Okay, yet that I don't know, that is difficult for me to understand, but just the broader idea is, like, let's say this one will go over here and this one will go like here. So whatever will happen, they will be always in complex conjugate form, that is for sure. Okay, and that's why they are symmetrical along this axis, right? Symmetrical. Okay, that's why I think I've already like gave you a few key points about symmetrical or not. If I haven't, so that will also be taught, right? So that's why they will be symmetrical, right? Because they will have complex conjugate poles. So whichever path this one chooses, this one also choose. Now you might tell me, sir, like this blue can go over here also and this green can go over here also. Yes, it doesn't matter, it doesn't make any single difference. Okay, if you make this green over here and here, it doesn't matter, that doesn't matter at all. Okay, because they are only complex conjugate poles. Okay, and it doesn't matter which color you choose. So here, right now, okay, I will delete this one because this color is of no use for now. Okay, well, just what I will do is, okay, basically this is going to the negative infinity. So now, right now, I hope you got a bit of idea about the break away point. Now let's study about the break in point. Okay, let's study about the break in point. So what will happen to the break in point? So you learned about the breakup. Now there may be a patch up also, right? So at a later stage, both of you realize that no, it was not the correct decision, maybe we should sort it out, maybe we should patch up. So now they are going towards the patch up stage, right? So what will happen, this breakaway point will become break-in point. And what is the another thing you notice? What is the another thing you notice? Tell me. That I have mentioned, right, in this key point, okay, that breakaway point, for example, will exist on the root locus between two consecutive open loop poles, okay, with no open loop zeros between them. So here what do I see? That I will have two consecutive open loop poles, right? Because one root locus will go from here, another one will come from here, and at some point they will merge, some point they will converge, they will what do you say, merge, whatever you say, like they will come together at some point, right? So then they will break away. Okay, that is why we need two adjacent poles and no open loop zero between them. Okay, no open loop zero between them. That is important. That's why whenever you see a breakaway point, you will see two open loop poles. This more examples will do, and I will slowly also explain this part to you. Okay, so yeah, basically yeah, this lecture is already going very long, but it is about the breakup and patch up, so I hope you are listening very carefully, right? So now let's study about the break-in point. So break-in point will occur between two adjacent zeros. Now it can be a virtual zero also, right? So this is a zero and this is zero. So breakaway point, so breaking away from real axis, and this is breaking into the real axis. Okay, breaking into the real axis. Okay, so it is breaking into the real axis. So what will happen? Let me delete this one first. Okay, I'm not very concerned about this one. Okay, I'm concerned about this one. So they may come, I'm not overly very careful about how will they come, right? So one of the branches may come like this one, and another branches might come like this one. So you might ask, sir, they may come like this also, right? They may come like this, they may come like this. I'm not overly concerned with that, because this is just a rough sketch that we do in hand, right? But in actual practicality, we plotted this in machines and MATLAB and all those things. So there it doesn't matter, like it will plot it perfect, but we are not plotting it perfect. Just the basic idea we want to get, and why I will explain you with a question. Okay, at the end after plotting this sketch, why we need a basic idea of this root locus while sketching from hand. So sketching from hand will be very fast. That's why don't need to overly bothered with how exactly my poles will be present where in the complex conjugate plane. Don't need to be overly bothered. Okay, I hope you got it. So they may come like this one. So one of the branches is coming like this one, the green one, and the blue one is coming like this one. So what will happen? Like they will be always complex conjugate, and at some point they will meet, right? Some point they will again come to real axis, because this part is present on the real axis, right? This part is on the root locus. So if this part is root locus, so they have to come together at some point, because we have only two branches. So those two branches are away from the real axis, but they have to come together at some point to meet here and again be together forever. So again, like the root locus should be present over here, right, in these points. So that's why they have to come together, right? Now if they come together here, again the same thing, right? Two poles will be present over here. Okay, I will copy this one. Two poles will be present over here. The multiplicity will be 2, and what happens? They converge. Conversion happens. Okay, basically they converge, right? Instead of diversion, what can I say is they converge. They converge basically, right? They converge. Now as they converges, hence it's a breaking point. As they converge, it is called a breaking point. As they converge. Okay, so I hope you got the basic answer, right? So why is this a breaking point and why is the breakaway point? And as you can observe, is this will be always between two open loop zeros, because as they converge, then they will again go away and terminate to zeros, right? So that's why they are coming from the complex plane. So they are coming from the complex plane to real axis to converge, right? Converge. That's why it will always between two open loop zeros. We'll do more examples and slowly we'll understand. Now, what is the important point? The important point is, what is the common thing between my breakaway and breaking point? The common thing, if you say always two poles are present, that is common. Two poles of what? Two poles of CLTF. So I should write this also. I hope you are not forgetting, right? This root locus is for closed loop transfer function, CLTF. So everything is CLTF here. Everything is CLTF. So two poles of CLTF. I should write this, else you will get confused. Two poles of CLTF are present. Okay. Here also two poles of CLTF are present. Okay. So yeah, I hope you got that. Now, if two poles are present, what does that mean? Two poles are present, like they are at the same location. That means my multiplicity is 2 again. So I have repeated poles. So common thing between my breakaway point and breaking point. What is the common thing? Common thing is basically I have two repeated poles. Okay, am I writing this spelling wrong? Two repeated poles. So if I have two repeated poles, that means basically multiplicity of 2. Now why am I concerned with this one? I'm just giving you an intuition to the proof of the relation that we'll get to find breakaway point. So generally you will given directly the formula, but why you won't be given, right? Why? That's why I'm like explaining you so much. Okay, so multiplicity is 2. Now what do you mean by multiplicity? Multiplicity means the number of repeated poles. So let's take, for example, I have example of multiplicity. So let's say I have a polynomial p1 of s equals to s plus 3 into s plus 4. Okay, now how much multiplicity does this have? One only, because every one has only one pole, single pole, none of them are repeated. So if I differentiate this polynomial, right, with respect to s, this will be s plus 4 plus s plus 3. Now let's say I want to check the value of the differentiation at one of my poles, right, s equals to -3. So if I want to check this one at s equals to -3, what will I get? Copy this one and paste this. I get, like, I put s equals to -3 over here, this is 1 and this is 0, so this is 1 only. Now if I name my second polynomial as, let's say, now I have multiplicity of 2, so this has multiplicity of mu equals to 1. Mu is known as the multiplicity, basically mu equals to 1, and this has, let's say, I have two poles at s equals to -3, basically s plus 4, and this time, right, mu equals to 2 for s equals to -3. Okay, s equals to -3. So now if I differentiate, right, if I differentiate p2 dash equals to 2 into s plus 3, simply s plus 4 will still come over here, and this will be s plus 3 whole square, right? Because first UV rule, right, I will differentiate this one and then I will differentiate this one, so only this one will remain, right? So I hope you understand the UV rule. So yeah, this is s plus 3. Now what I will do, basically, now if I find my p2 dash at s equals to -3, what do I see? I see 0. Okay, so that is the property of multiplicity. Okay, that is the property of multiplicity. So what is the property? Property is, if we have a polynomial of multiplicity 2 at a particular pole, then its first derivative will always be 0 at that multiplicity. Then its first derivative will be 0 at that multiplicity, okay. So like proved it here also, but this in general is true if we have mu multiplicity, right? If we have a polynomial with multiplicity of mu, okay, I can say this as, now I will write this mu, okay, I will write this mu. So 2 you have understood, but I will write the full actual statement, mu, then its mu minus 1 derivative will be always 0. Instead of first, I will what I will write is mu minus 1. Okay, I will understand, right? So if I have multiplicity of 3, if I do the second derivative at that location, put the value of pole, like put the value of s at that location, it will come out to be 0. So this is the basic property of multiplicity, and that is what exactly we'll use. Okay, now let's come to the basic intuition only. So what we know my g of s, we know my OLTF, basically g of s into h of s equals to k into a of s by b of s, right? A of s into b of s. Now if my a, like what will be my a of s? let's remove the standard formula. So what was the not the formula, standard form? So a of s was basically m number of zeros. So it was something like this one, right? S plus z1, s plus z2, and it goes on till s plus zm, right? I have m number of zeros. Now what is my b of s? I'm really sorry for the disturbance. What is my b of s? B of s, I have n number of poles, right? So if I have n number of poles, it becomes s plus p1, and it goes on. I will not write this much. S plus pn, right? S plus pn. So this is what my b of s is. Now what is my closed loop characteristic equation? My characteristics equation is this one, right? Is 1 plus a into s divided by 0, right? This is what my closed loop characteristics equation is. So now what is my closed loop polynomial? So this is what basically my closed loop polynomial is. Let me name this as my closed loop polynomial. PCL, which is equals to 1 plus k a of s by b of s, right? This is my closed loop polynomial. Now if I differentiate this one, okay, this is my polynomial, right? This is my polynomial, as I mentioned here, right? This was my polynomial basically, okay, closed loop characteristic polynomial. If I differentiate this one, what will I get? Okay, that is the characteristic equation that I am interested in. So that is how I get my closed loop poles, right? From here, from this equation, I get my closed loop poles. So I name this as PCL and I differentiate this one, okay, just for using the multiplicity property, okay. So if I differentiate this one, what do I get? P dash, oh, let me, equals to 0 plus k upon, like this is like u upon v formula differentiation, b dash of s into basically this will, no, sorry, this is not b dash, this is b square of s into basically this will be a dash of s into b of s minus a of s into b dash of s, right? So okay, let me now write the s very carefully, because this is not looking like s, this is looking like something else itself. This is s, this is s, okay, yeah, these are s only, fine, sorry for this one. So all this will be s only, and this is also s, and this is also b dash of s, okay. So basically, right, this is the differentiation of my PCL, okay. So now what we know, my break in or away point can't lie at k equals to infinity or k equals to 0. Why? Because there needs to be repeated pole basically. But here, what do you know? We don't have repeated poles, right? On a break in and break away point. So that's why we can't, k can't be equals to 0. Not possible, right? Because first of all, that doesn't make any sense, and we don't have repeated poles at basically that open loop poles, right? So that we first considered. So no repeated open loop poles. No repeated open loop poles we have, right? So hence, if you don't have open loop poles, so k equals to 0 will not yield me any break in or break away point, okay. So k can't be equal to 0, that is not possible, okay. So this I have to make 0, right? This I have to make 0. Why? I forgot to tell you the main thing. This I have to make 0. Why do I have to make 0? Because I know that there is multiplicity at s equals to sb, okay. It can be breakaway or break in. So as I know, like PCL dash y, this will be 0, PCL dash y will be 0 at s equals to sb, it will be equals to 0. Why? From here, from this statement, okay. just go back to the video and see that if I do the derivative of any polynomial, right, if it has a multiplicity, it will be 0. So here that property exactly what I'm applying, right? It can be either break in or break away, that we will understand later, but it has to be 0, okay, for it to follow the property of multiplicity. As follow the property of multiplicity. So it will follow the property of multiplicity. Okay, so this is the first case that k can't go to 0. Okay, that we understood. So I should write this one later. Sorry for like not going in the sequence. Basically, first I should have told you that this will be equal to 0. Why? Because it follows the property of multiplicity. Now then I should have told you that k can't go to 0 because I know I don't have any open loop repeated poles. Okay, or in general k we don't take it as 0. Okay, we don't take it as 0. So now what else can satisfy this equation? Like this numerator can go to 0, that is one case, and this numerator can go to infinity. So let's take the second case. So can my denominator b of s go to infinity? So if b of s goes to infinity, if b of s goes to infinity, what does that mean? So b of s is basically poles, right? Poles of the OLTF. So can it go to infinity? Again, if it goes to infinity, it means k is 0, right? K is 0, which is not possible. So b of s can't also go to infinity. Okay, if b of s goes to infinity, what does that mean? That means basically, what I'm saying, if b of s goes to infinity and not poles going to 0, if b of s goes to infinity, that means my s is going to infinity. Basically, let me write this down here. Let's say I have one example, k into s plus alpha divided by s plus beta, right? Now this is b of s, right? This is my b of s. Now if this is going to infinity, what does this mean? Like this beta is constant, so s has to go to infinity. So if b of s has to go to infinity, okay, if b of s has to go to infinity, that means s has to go to infinity, right? S has to go to infinity. Now if s has to go to infinity, what does that mean? That means asymptotes, right? And my breakaway or break-in points won't lie in the asymptotes. Okay, we only lie in the between two poles or two zeros. So for this case also, like not possible, because my breakaway or break-in point will lie between two asymptotes, two poles or zeros. My breakaway slash two asymptotes. Okay, so yeah, two asymptotes. So yeah, that is basically what my breakaway and break-in point condition is, and this won't be possible because it can't lie on the asymptote itself, right? It can't lie on the asymptote itself. It has to lie between those two. Okay, so now what condition is left? Only this condition is left, right? Only the numerator one. So this, right, no one will prove. Okay, they will directly go into the equation. So I'm still proving it to you, but if you don't understand, don't worry. Okay, this lecture has already gone long, so maybe I have to stop this here only. Okay, how many more steps we have left? We have still left quite a bit of step. So yeah, so like this is the conclusion. Basically what I will do is, like this lecture is already gone long, so the remaining steps I will do in the next lecture. And for now, you just understand like what is breakaway and breaking point and what is the condition. Now what is the homework for you? Find the condition of value of s for which I will get like a breakaway or breaking point from here, right? Hint is just look at the numerator, and then solve further. Okay, so yeah, and also find the breakaway and breaking points using this equation for this current example, right? That we are solving. This is the homework for you. Okay, so yeah, thank you for watching and see you in the next lecture.